Hello everyone. So today we are going to discuss about design of short column, but today we will be having uniaxial moment applied to the column. Okay, that means so far what we have discussed a short rectangular column, right, where there is only point load P, and we have take care of minimum eccentricity E minimum, and we have seen that most of the cases the minimum eccentricity lies well below than 0.05 times of the lateral dimension. So the moment that should be taken into account, if E minimum is more than 0.05 of the lateral dimension, that moment is so far we have not considered. Okay, so all the problem that we have discussed, those are basically because of only designing of column using axial load. No moment we have considered so far. We have discussed rectangular column, short column basically, and circular column. These two we have discussed. Okay, so now today we will see that if this condition is not satisfied, that means if this is not satisfied, that is E minimum is more than 0.05 d. I told you that if this is the condition, then you have to consider the moment, which is where moment becomes equal to P into E. Okay, that means moment should be taken into account, or it is not like that always. Only the minimum eccentricity will contribute towards the moment. It is not like that. Because of the frame uh, action, the column might have some additional moment to it. Okay, suppose this is a frame, these are the beams. Okay, suppose these are the beams and these are column. Okay, these two are the columns, these two are column. Let me show it by blue color. So these two are the column. Okay, now when there will be loading, suppose these are the beams. So when there will be loading, so the beam will deflect, right? So a moment will come here. The moment will come from all the sides. Okay, so these moments, if these are not balanced, then this will in turn apply a moment to the column. Okay, I think you have studied about um, cantilever method or portal frame method, where you have studied that how the moment is being transferred from beam to the column. Okay, so if you have a suppose frame, you have a building frame, and suppose the plan is something like this. In this case we have suppose columns over here, 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 like this arrangement of column is there. Now when there will be when there will be loading over the whole frame, the beams will get deflected, so there will be a moment from the beams, right? So this beam will have a moment. Suppose I'm drawing it something like this. Suppose this is the moment, and this will be having moment. This beam will be having moment, and this beam will have moment. Similarly, this all the beams will be having some moments in moments, right? That is, you have already studied. So like this, the moments will be there. Now the thing is, if you see that these moments, if these are not equal, that means suppose this is m1, this is m2, this is m3, and this is m4. Okay, if suppose algebraic sum, you have to take care of the sign. Okay, so you're taking care of the sign. If you take the algebraic sum of m1, m2, m3, and m4, if it is not equal to 0, sorry, you cannot actually we can have, you can think it of in the two axes. Let us consider two axes. That will be easier. Suppose this is the x-axis, this is the y-axis. if I'm talking about moment about x, then it will be m1 plus m2. I'm telling you again, this is algebraic sum, okay? And my will be m4 plus m3. That means you have to consider the sign, whether it is clockwise, it is anti-clockwise, that means it is positive, it is negative probably. So that means that you have to take it into account, but you will be having two moments in the mx direction and my direction. If m1 and is equal to m2 and m4 is equal to m3, or these are suppose equal, or I'm saying in equal and in opposite sign, that means if it is clockwise, the m1 is clockwise, m2 is anti-clockwise, or m4 is clockwise, m3 is anti-clockwise, then what will happen if m1 is equal to minus of m2, m4 is equal to minus of m3, then this mx will be equal to 0. This mx, this will be is equal to 0 and this will be 0. In that case there will be no external moment to it. But if it is only possible if all the moments m1 m2 or m3 m4, these are equal, and this is only possible for a very symmetric kind of structure. But if you see this column, this particular column, here you can see that this column is having a moment in the x direction. Suppose this is 5, 6, 7. Okay, so in the mx direction we have m5, and in the my direction we have m6 plus m7. Okay, I'm again saying it's algebraic sum. We have to take care of the positive and negative sign. Means if m6 may be positive, or m6, in that case m7 will be negative. Okay, so if you see here, there is no chance of having mx is equal to 0. It cannot be 0, right? It will be having, always it will be having a certain amount of moment, but probably my, it might be 0 if m6 is equal to m7. Okay, in that case probably in the my direction it might be 0, but mx cannot be 0. So the columns which are at the edges or at the corners are always subjected to moments. Okay, now if you see this column, this particular column, then it is, if I say that it's a very perfectly symmetric building. Symmetric means all the beams, column sizes are same, all the spans of the beams are same, everything is same. In that case you can say that m6 is equal to minus of m7, and in the column of this column, if I say here mx will be m5 and my will be 0. So in this case this column will be designed as a uniaxial moment. Okay, uniaxial moment will act. Uniaxial moment will act. Okay, so that means only in one axis your moment will be acting. But if you see, if you take, now suppose if I consider some other column, suppose this corner column. Okay, if I consider this corner column, you see this column is having moment in both the directions, in the x direction and y direction, and this cannot be neutralized by some other moments, because there is no member this side or this side, so no member will be there. So this member, this column will be having a moment in the x direction and moment in the y direction. Mx and my both will act on this column, so it will be biaxial moment. Okay, so this column probably it can be designed with a uniaxial moment, and this column probably designed with a biaxial moment. So the design process is similar. If you take care of biaxial moment, you have to take care of one axial, means either mx or my at a time. First suppose you take mx, then you take my and design it accordingly, and you just find out for which case both the moment are being satisfied or being taken, or are being taken by the column. Okay, so there are certain rules regarding this in the IS code, so you can follow that. But for today's class we will be looking for a column which is probably somewhere at the edge line where there is only one moment is there, and other side probably it is zero. Okay, I'm using the term probably because in reality it might not be the case. In reality you will see that most of the cases it is a case of biaxial moment case, because means in reality in your houses probably these are not always symmetrical. There is always some holes in the slab. There are the spans of the beam or the columns are not same, so there is always some irregularities are there. So because of that most of the columns are subjected to biaxial movement. That means both mx and my exist. But for being a very ideal case, suppose this is the ideal case I'm taking. In that case only one axis, we have a moment in only one axis. This may be because of this frame structure or maybe because of the minimum eccentricity. Probably it can be from any of the cases. It might be from minimum eccentricity or it might be because of the frame. Okay, so the design that we will be solving today, that will be for uniaxial moment. Okay, I hope you have understood this. So to, so now let's go into some theories. So so here I have mentioned some cases. So case 1 says that concentric loading, zero eccentricity or or nominal eccentricity, that is xu is equal to infinity. See, just remember the beam problem. The beam is not subjected to any axial forces. It is only subjected to some moments, right? So because of the application of the moment, we have found out what is the stress distribution diagram. It is something rectangular or on the initial part, then it becomes parabolic, and the strain distribution is diagram is perfectly triangular, which having maximum strain of 0.0035. It is a maximum allowable stress, and at the rectangular portion we have a strain of 0.002. Probably you have remembered, and the maximum stress is here 0.446 FCK, and the neutral axis depth is represented by XU. So everything that we are going to use today. Now see, the columns are supposed to be a compression taking member, right? So that means only there should be only compression. But now just now we have seen that the it is not exactly happening in the practical life. In real life we will be having, along with the axial force, we will be having moments. Okay, we will be having axial force and moments. Now the thing is, axial force can be taken, that is no issue in that. That is F by A you can do and find out the stress, and that stress should be taken care of, that is fine. But how to take care of the moment? The moment, if you want to take care of, you have to refer to the beam. When how you have taken the moment in case of beam, the same process you have to follow in case of column also. So that is why here the eccentricity, the nominal xu term is here. You can see xu means nothing but the depth of the neutral axis. So if the case is, the first case is to that, if suppose we have a column over here and this is the suppose center, and the okay, so this is the center, and you have a point load pu over here. In that case what will happen, is there an eccentricity? No, there is no eccentricity. All right, eccentricity is zero. Or you can find out E minimum also. E minimum you can take it as per the IS code. The minimum E minimum you have to take as 20 mm, but if it is less than, it is less than 0.05 of D, then it is okay, right? So that is why it is mentioned that concentrate load, that is zero eccentricity, this is the case, or nominal eccentricity, that means E minimum is less than 0.05 times of D. This is considered as case 1. In case 1 what we do, we have only axial force, right? There is no moment is not there, sorry, moment is absent. Okay, in this case what will happen, that all the stress, if I draw the stress distribution diagram, it will be a perfectly rectangular stress distribution diagram. It will be something like this. Okay, if this is the cross section, if I see from the top, it will be says dot 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 dot. pi. That means the forces are acting from the top at the section, okay, as it is column. So it is a rectangular distribution. If I draw the stress distribution, it will be a rectangular distribution, okay, equal distribution. And what will be the value of the stress? The maximum value of the stress that you can allow 0.446 fck. This much of stress you can allow it here, right? So this is for the first case. That means when eccentricity is 0 or nominal eccentricity is there. So this is the case. Only stress is perfectly rectangular. It is the same all along the cross section. Now see, check the case 2. When there is a moderate eccentricity, that means when xu is greater than d, that means suppose you have a small eccentricity to the member, okay. So I think we have some figures, so I think it will be better if I go through those figures. So case 1, I have already told you that E is 0 and E is less than E minimum. In that case, it has been mentioned that the maximum stress that you can have, it is 0.446 fck, and you know that the rectangular portion begins from 0.002 of strain. So the strain is basically 0.002 everywhere. The maximum strain will be 0.002 and the maximum stress will be 0.446 fck. This is the case for E is equal to 0 if there is no eccentricity, okay. Now moderate eccentricity, that means neutral axis outside the section. What will happen? Just think of it like this. Suppose you have a plank, okay, and you are just floating on water, okay. You have a plank and over which you are floating. So suppose this is you and this is the center, okay. This is L by 2 and this is L by 2, okay. Now if you are at the center, exactly at the center, what will happen? The stress will be uniform. It will be just the upward stress, the water, the whatever upward reaction the water gives to the plank, it is same, right? And this value will be how much? If your weight is W and suppose I'm talking in terms of a say uniaxial case, means only one dimensional case, then if this is the length, then the stress will be W by L, right? I'm talking about only in 1D case. Suppose only one dimension I'm considering, the width is, the breadth is, I'm not considering, okay. So it will be perfectly rectangular. It is with the stress will be W by L, the total load divided by the length, right? But now suppose you are over here. Now what will happen? The stress distribution will be like, it is not will be what, rectangular. If you are here, so here your reaction will be more, right? And here it will be less. So it will be somewhat like this, a trapezium, okay. It may be somewhat like a trapezium because you are here. So if load is over here, the reaction will be maximum over this side, so it will be having maximum reaction just below the load. So the maximum reaction is over here and minimum reaction is over here, okay. So in this case, what is happening? If you see the neutral axis, if you extrapolate, it is just outside the section, right? If you go for like this, it will be the neutral axis. So it is just the stress distribution diagram. You can, if you see carefully, it is just nothing but a stress distribution diagram. See, just the stress distribution diagram, right? So if this is upward force, so there will be downward force, and this is the neutral axis. This is nothing but the xu. Suppose this is xu. So if this is the case, that means if xu is outside the section, what is happening? that all the section is under compression, everything is under compression. So that is what it is mentioned is neutral axis is outside the section. That means this is a neutral axis, this neutral axis is outside the section, so all the section is under compression because it is compressing the plank, right? So here if you can see similar thing here, if there is a small amount of eccentricity because you are not at the center but you have shifted to certain distance, so this is the eccentricity over here. So if you have a small eccentricity, then you will be having certain moment, and you have a distribution, trapezoidal distribution. So the same distribution is shown here. So this is a trapezoidal distribution we am talking about. This is a neutral axis. Probably it will be tension over that. Means if you extend, then you might have tension over here, right? So this is a neutral axis. So if this is this gives you the strain, and this is a stress as we are designing for limit state. So that is why the stress distribution diagram is assumed to be rectangular and parabolic. If it is a walking stress, it would have been a perfectly triangular distribution. Okay, now now you can see that what are the values we can have as per limit state. The maximum Emax over is here, and if this is a stress distribution, maximum stress we can have is 0.446 FCK. And then after at a certain distance we'll be having you will start with the parabolic distribution, it will end here. This is the neutral axis, right? And where it is start, generally at the strain of 0.002, just like the beam. And this is a maximum strain, and what is the maximum strain value? It is basically 0.0035 minus 0.75 of E minimum. This value, this question sometimes comes, what is the E maximum value of E maximum value of that means the strain, maximum strain in case of a column, if suppose minimum strain is provided to you. If minimum strain is provided to you, if this is provided, something value is given, then you will be asked to find out what is the Emax value. In that case, you have to use this equation, which is 0.0035. It is supposed to be a maximum one minus a small amount, that is 0.055 of epsilon minimum. Okay, so this will be the maximum strain if this is related to minimum strain. Whatever minimum strain is over here, corresponding to that you will be having the maximum strain. Okay, because it's a triangle, right? So you can just draw, you can just find out using the similar triangle equation. Okay, so you already know that the depth is 3 by 7 of D. This is nothing new, so you already know about this. Then after that, suppose another condition, because these are conditions that you have to take care of, because you do not know whether how the moment is acting. It might be the moment might develop tool compression to the section, or it might develop tension to the section. So that is why I'm trying to make you understand this all the cases. Now case 3. So now initially we have pure compression, right? Initially all the section has same amount of compression, that is uniform loading is there, uniform strain stress you have experienced, first case. Second case, we have a trapezoidal distribution, but all the section is under compression. The third case is that the neutral axis is just at the edge. That means it is maximum at the one side and zero at the other side. But yeah, the previous case we had some values. Maximum means we had some values at the edge. That means it is not zero. The compression is not zero over here. But in this case, we are assuming that neutral axis is just at the edge. That means here the compressive force or the stress is zero, and here it is maximum. So see, this is the maximum value, so it is be 0.0035, right? And this is 0.002 strain values, and maximum is 0.446 FCK. So this will be basically used like understanding the why this is important is that suppose you have got the p value, some value, m value you have given to you, then you will be able to find out what is the eccentricity for the moment, and then you will be able to find out what is the depth of neutral axis, right? So according to depth of neutral axis, you might have to find out the stress, and in that case this diagrams will be helpful. So you have to understand whether it is outside the section, whether it is inside the section, or it is at the edge of the section. Then accordingly your values of the strains will be different, right? So that is why this is important. So in this case, if a neutral axis is just at the edge or just at the edge of the section, in that case maximum strain will be 0.0035 and 0.002, where the rectangular stress distribution diagram starts. Okay, 0. This is 3 by 7 D. So I think there is nothing to explain here. It is very pretty clear. Then the last case, which is very important one, that is neutral axis lie within the section. If what happens, like just like a beam, we have in beams the neutral axis lie within the section. So that is why we had some tension region, which we ignored, and we have a compression region, right? We have a compression region and we have a tension. This is the compression region, this is the tension region, and probably you have remembered that we have ignored the tension region. But here in the column also similar case might happen. What if the moment is such a, it is acting such a way that it is developing the neutral axis just inside the section. In that case, just like beams, we'll be having maximum strain over here 0.0035 at the edge, and the and at the end of the rectangular section is 0.002, and maximum stress, this stress is 0.446 fck. Now this is xu value, xu is less than d, you can see here. So if this is the case, you can see that a small tension is developing. That means what is happening, let me tell you by the same Planck um, problem, Planck example. Suppose now you were initially you were at a slightly moderate distance from the center, but now you are at the very far away from this, E is very high. In that case, what will happen, your Planck will move like this, right? You will go down and this side will go up. Why is that so? Because it is going up because we will be having tension there, and this side will be compression and this side will be having tension. So the same case is happening. It is not in contact means what? There is no force. There is no force, that means it is under tension, or opposite forces are being developed, right? So similar cases here, this side will be having the compression and this side will be having the tension. So this is for neutral axis lying within the section. So small theory questions you can expect from all these distributions, or how means what are the stress distribution diagram, or how it is a strain distribution diagram, and these are basically will help you to understand and to formulate the equations to solve the column problem, which is subjected to moment and axial force as well. Now the one thing is very important, that so far we have discussed that we have initially pure compression, then we have compression, that means initially we have a very pure rectangular distribution, right? Then we had a trapezoidal distribution where where the stresses are gradually decreasing and we had certain value. Then we had a distribution where it's like a balance case where it is maximum at one edge and zero at the other edge. Then we have another case where the compression is on one side and tension in the other side. So this kind of cases, you can see that it is gradually the from compression to tension, it is now changing. Now you can see that this, if the column is, we are talking about all about the column. So if you say that this column, about this column is definitely going to fail by compression, this column is also going to fail by compression, this will be also fail by compression, but this will be a balance failure, and this will be this might fail by tension. Okay, so all these conditions that so far we have discussed can be summarized within this particular graph. You can see uh, now this graph is having two axes. One is basically, say, let us talk about only, just look at the p value, that means this is the axial force and this is only the moment. Okay, on this side we have only p value, that is axial force, and this side only we have moments. And in that case what happens, that if, and this shows that when the moment is zero, when moment, at this case the moment is zero and we have maximum value of p, that is the axial force, then it is mentioned that is only axial load. there is only axial load over here. Okay, and then as we go on this side, the moment goes on increasing. At certain point, what happens? The bending means there is a means okay. Uh, you will having the p value and the m value will be same, and then it is go on increasing. Then at certain point, we will be having the balance failure. That means we will be having the case of this. That means pure sorry, in this case balance failure means will be compression as well as tension similar, so both cases will be there. Okay, and the failure is both, it means the compression and tension both are at the, means both are at the ill level. Then we will be having the tension failure. That means the compression phase is very less but the tension phase is very large. In this case, what will happen? The failure will be tension failure. So what does it say is that this side, if you see here, it is not is P, but it is P by FCK BD. This is basically FCK is the grade of concrete, B is the width, and D is the depth. So it gives us a value that is P by FCK BD, which represent the axial force, and mu by FCK BD square, mu by fck bd square, this represents the moment. These are non-dimensional quantities, so as we are comparing, the one is having a dimension of kilonewton and other has a dimension of kilonewton meter, so it is not exactly very convenient to compare some to other to two values which have different dimensions. But if I compare with a non-dimensional value, it becomes more accurate. So P by FCK BD, this is a non-dimensional, and mu by FCK BD square, these two are the non-dimensional values. Mu by FCK by BD square represents the moment factor, and this represents the axial load factor. So as you can see that when moment becomes zero, in that case only axial load is there. Only that means eccentricity is zero. As you go on this way, you can see that eccentricity is zero over here. Then eccentricity goes on increasing. Okay. As eccentricity goes on increasing and like this, and here the eccentricity becomes here p p p is not, means only p value, that is axial load is not there, only moment is acting. Okay, so here e sorry, yeah, here e is 0, here e is maximum, here e is minimum. So or e is equal to 0, e is 0. Okay, now if you remember the e minimum, we talked about e minimum, which is 20, minimum of 20 mm. You can see that we will be having it if I say e minimum, because here e is 0, so if I say e20, so it will be somewhere here, right? So this is suppose e minimum. So if this is the case, here you can see this is purely axial failure, because this is compression failure. Compression failure will occur up to this point. All this point you will be having compression failure, but only even if you go from this side, this end, you will be having the tension failure. Tension failure means what? Compression failure means it will be crushing, you will be crushed, but tension failure means it will be splitting. The column will be split up. Okay, suppose the load will be somewhere here, so it will be split up here. But here all the compression failure means the loads are in the acting downward, means it is trying to crush the column. Okay, in the tension, what will happen? It will act in the opposite direction, it will try to split the column. Okay, so tension failure is occur only after the B point. That means if eccentricity is go on increasing at this, here it will be having the maximum eccentricity, after which if you go on increasing the eccentricity values, you will be having the tension failure, and this is the compression failure. So from here to here, so we can expect to a certain value of eccentricity, we can design it to be purely compression. But other than that, both P and M both are very important, and up to this value, means within this range, e minimum to up to suppose valence failure, this is important. Here both P and M are equally important, both are equally important, both are equally important, so you have to consider both axial force and moment. Okay, and if, as you can see, this graph is very important to us, because this graph helps us to find out at what P by FCK BD value, what MU by FCK B value should be there. Okay, and this actually helps you to understand or find out the what to say, the AST value, that means the area of steel, percentage of steel, you can find out from this. Okay, so this graph is called nothing but is called interaction curve. This is called interaction curve. This is only 2D because we are assuming that, suppose if this is the column, P is only acting along the axis. That means P is over here or here or here or here. So it is acting along the axis. That is why only one graph you are looking at. But if you say, suppose P is somewhere here, both X and Y are there, so it becomes what? It will be now, in that case, it will be in a 3D diagram. Because if in that direction, we will be have to consider the X and as well as the Y, means Y direction as well. So eccentricity in the X direction, AX and EY, both you have to consider. In that case, this interaction diagram will be a 3D diagram. It will be a 3D diagram. It will be just like a shell. Okay, it will be just like a shell, something like this. It will come here, here, like this. It will be just like a shell. So this diagram is very important, this interaction diagram. You can actually develop this interaction diagram if you are interested. You can study the Pillai Menon book, where for a particular column, for particular suppose having certain dimensions, certain P and D and FCK values, if for different P, what is for different point load and with different eccentricity, you can find out what are the moment it can take. Okay, so if this is the P value, this much a moment it can take. That means, so that if this is the P value it can take, in that case this much a moment it can take for being in a compression failure. Okay, so tension failure is not at all acceptable in case of concrete, because we know that concrete is very weak in tension, so we cannot go beyond this balance failure. So all your designs will be lie within this range. Okay, so this is out of context, out of question, so this should not be there. Only thing is this much, only this region should be taken for the design. So column subjected to varying magnitude of P and M will act with its neutral axis at varying points. So in that case, this is the diagram. So please go through the book Pillai manner, probably you will understand. Yeah, this figure that I have taken, that is from Pillai Manon book. You can see here. That means PU naught or PUO. This represent that where eccentricity is 0. Okay, this one point, and one dash point is where that is eccentricity is E minimum. Within this region you can see that moment is very less. If you consider the moment also, the moment is very less. The moment according, means as per this whatever point load it can take, means axial load it can take, corresponding moment is very less. So that is why we have ignored that particular means if the E is less than E minimum, we ignore the moment, because it becomes very less, is very less. M is very small. Okay, it's small value. So we, as this is within this region, as you can see, moment will be very less. So within this region we do not design for, or we do not take care of moment. But after this, if 1 dash to 2, you can go to, if you go on increasing value your value, you have to consider the moments. Okay, so this is the balance failure case, when and after that you will be having the tension failure case. This is the balance failure, so where E is equal to EB, that means the eccentricity for balance failure, and here E is equal to infinity. That means your, suppose this is the column and your point load is not here but somewhere here probably, that means only moment is acting. Okay, so that means only all of the tension will act on the column. This is the balance failure. So if someone asks you what is the condition for balance failure, if E is equal to EB, right? If it is less than EB, then it will be a compression failure. If it is greater than EB, then it will be a tension failure. Okay, so this particular interaction diagram is very important. You can expect a small question in your exams where asking to explain this interaction diagram. Okay, so I hope that you have understood. After this, but the theory is very long. Probably you have, I mean, you might have understood that I have mentioned so many things. But if you go for design, you will surprised to see that the design is very easy, because we will be taking help of this interaction diagram. We'll be taking help of this interaction diagram. So one thing that before going to this, we should discuss about a particular special publication of Indians Bureau of Indian Standards, that is SP16. This is for basically the designing. It has all the tables, all curves for designing beams, columns, slabs, etc. So SP16 provides you this interaction diagrams where for different P by FCK BD and MU by FCK BD square values, what will be the percentage of steel required. So you can directly refer to that, and you can download this particular code or SP16 from the net. It is available freely, and you can refer to that for learning purpose. It's for as far as you are in the you are using, not for any commercial purpose, there is no issue. You can learn it, you can see how to use SP16, and I would suggest that you please download this and refer to the code, refer to this code. And this is not exactly code, this is just a design aid to IS456. So I hope you will download it and take a printout of it. If it is a very huge, means probably more than 400 pages are there. No need to print everything. You can take the print of only the column portion that is important for us for the design or as per your syllabus. So other than that, the remaining portion no need to print. Okay, so let's look at the problem here. The question says design an RC column working axial load of 1500 kilonewton. The size is given as 300 mm by 400 mm. It is unsupported length is 3 meter and M20 and 415 grade of steel. The column is fixed at both the ends. Okay, so if you see the column, the problem is basically similar to what we have discussed in the previous rectangular column design problem. Okay, so you will see that we have the moment is not given to us, but probably the moment will come from the minimum eccentricity criteria. So let's see. So let's see the data which are available to us. So this is the problem. Okay, this problem, this figure is wrong. We have this side is 300 and this side is 400. Okay, this side is 300, this side is 400. Please correct. Okay, so here dx is 400 and dy is 300. So if I say what is the cross area, which is dx into dy, which is 1.2 to the power 5 mm square. The working load is given, that is 1500 kilonewton, and unsupported length is given. So most of the things will be similar. That first of all, you need to check whether it's a short column or long column. Then you have to check for eccentricity. All these things will be similar. The only thing that we have taken means in excess of what we have done in rectangular column design is that we have calculated the the d dash value. The d dash is nothing but suppose this is the column. We have this. These are the bars, and whatever is the clear cover that is provided, sorry, effective cover that is provided, that should be taken as d dash. Okay, so d dash is nothing but the effective cover. So for column, basically we take 40 mm. Most of the time we take 40 mm clear, means clear cover, then 8 mm of stirrup, and 16 mm, so suppose assuming 32 mm bars, so 16 mm I have assumed. So it is 64 mm of d dash that we have taken for our design. So now, um, first thing is that is same, that is we have to check for the short and long column. So I think there is nothing to explain over here, so everything is already known to you. Then this is a short column, basically the L effective by dx and L effective by dy, which are both are less than 12, so it's a short column. Then we have to look for the minimum eccentricity. Here is the, means the only difference that will come is here, that is you have to find out the minimum eccentricity. So x minimum is basically so x minimum, you can see L by 500 dx by 30, which is around 19.33, and minimum is 20 mm that we have to assume, and ey minimum is also coming out to be 16, and y minimum is also, we have to take minimum 20, right? It should not be minimum of 20 mm to be taken. So x minimum is 20 and ey minimum also we have taken as 20. Now we have to check that whether this minimum e minimum is less than or greater than 0.05 times of lateral dimension. That check we have to done, because that check will tell you whether you have to take the moment or you do not have to take the moment. Okay, so if I do that, 0.05 times of dx, it is coming up to be 20, and 0.05 times of dy, it is coming to 15. And if you see that it is exactly 20, so there is nothing to worry about. But here you can see that 0.05 times of dy is basically less than ey minimum. Ey minimum was 20 mm, right? So it was 15 mm, 0.05, the y is 15 mm and e minimum is 20 mm. So e minimum is ey minimum is not less than this 0.05 times of dy. So that means what? If any of this condition is not satisfied, that means if as this condition is satisfied, so in this x direction, about x direction, the moment will be not there, but in the about y direction, movement will be there. So hence 39.3, this clause or this equation cannot be used, as the minimum eccentricity is more than 0.05 times of dy. So moment will also act in the column along with the axial load. As this condition is not satisfied, so we have to consider the moment for this particular design problem. Okay. Be careful about this step. And now suppose you have in both the cases you will be having if the suppose here we having 0.05 times of dy is basically less than e minimum, ey minimum, and if in the x direction also, if this condition is happening, like 0.05 times of dx is less than ex minimum, in that case also we have to consider a moment in the x direction, about x direction also. That means if this is the column we have, this is x and this is y, now the moment that we are considering about y, that is this is my, because it is about y. You just think about y, the moment is acting about y. Okay, and if as for our condition, as 0.05 times of dy is less than ey minimum, so my is going to act. If 0.05 times of dx is also less than ex minimum, in that case mx, which is acting about x axis, also should be taken, and then it becomes a biaxial moment problem. Then it will be a biaxial moment problem. But here only in one side we have to consider minimum eccentricity, other side we do not have to consider minimum eccentricity, so it will be a uniaxial problem, so mx will not be present. Okay. So that is why this is a uniaxial column problem. Now let's find out a factored load.
So P is fine, that is 1.5 times of whatever working load is acting, that is 2.25 into 10 to the power 3 kilonewton. And what will be the moment now? My will be Pu load into the eccentricity. That will give you E minimum. Okay, E minimum eccentricity that is there, that will be 45 kilonewton meter. Okay, so this is the moment that we have to consider. Now we have one axial load value, one moment value. Both values should be taken into account for design. Now, how to design it? So the designing, if you see clause number 39.5, members subjected to combined axial load and uniaxial bending, both are there. This is the case where combined axial load and uniaxial bending both are present. So a member subjected to axial force and uniaxial bending shall be designed on the basis of 39.1 and 39.2. And note, the design of members subjected to combined axial load and uniaxial bending will involve lengthy calculations by trial and error, because we are not very sure at what value, means the different values or different eccentricities will be having different moments, right? And the whole process of solving this problem is very lengthy. So in order to overcome these difficulties, interaction diagram may be used, that just now we have discussed, and these have been prepared and published by BIS in SP16 design 8 of reinforcement concrete of IS 456. So that is why we are going to take help of the SP16 to simplify our problem. Okay, so let's see. Yeah, it has been mentioned here that if it has been it has been subjected to both axial load and uniaxial bending, then you have to refer to 39.1 and 39.2. So what are those clauses? Let's see. 39.1 assumption says that in addition to the assumption given in 38.1a, that means this conditions. Now 38.1a to 38.1e, for flexure the following shall be assumed: the maximum compressive strain in concrete in axial compression is taken as 0.002. You remember just now we have discussed different conditions for columns. You have remember that maximum stress is 0.0035, right? And here the maximum compressive strain in concrete, you see here in the column, your maximum strain should not be more than 0.002. It has been mentioned. That means in no case your strain should be more than 0.002. That you should be taken into account. And the maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, and when there is no tension on the section, shall be 0.0035 minus 0.75 times of the strain at the least compression compressed extreme fiber. See, this is what we have already discussed. That means if there is only compression, the maximum compression in concrete in axial compression, that means only axial compression is there. Just try to remember what we have discussed in the initial few minutes of our lecture, that if that is load is only, or there is no moment, only axial load, then what we have to say, that it will be a uniform distribution of load. And if you remember the stress distribution diagram we have seen, or the strain distribution diagram, we have seen something like this, right? It is a perfectly rectangular, and I told you that maximum strain is 0.002, and this is as per this clause. Okay, it 39.1a. So this clause says that if it is axial compressive completely axial force is there is no moment, then strain should be taken as 0.002. And if the maximum compressive strain at the highly compressed extreme fiber in concrete subject to axial compression and bending, and I also told you that when there is an axial load as well as bending moment, both are acting, that means we are having a distribution like this. In that case, you will suppose this is the column, and we'll be having E minimum over here, and we'll be having E maximum over here. And what is the E maximum value? This is mentioned, it should be 0.0035 minus 0.75 times of the strain at the least compression extreme fiber. Remember, I told you that is 0.0035 minus 0.75 of epsilon minimum. Okay, clear? So these are taken from these two clauses. Then minimum eccentricity, this also already we have taken. All the members in compression shall be designed for the minimum eccentricity in accordance with 25.4, where calculated eccentricity is large, the minimum eccentricity should be ignored. That means suppose everywhere you will be taking care of the minimum eccentricity, but suppose x means in this question I have already only given you the axial force, which is 1500 kilonewton. But if in the question also moment is given like 50 or 60 or say 100 kilonewton meter already given to you, in that case the moment due to minimum eccentricity is only 45 kilonewton, right? Then you can just ignore it, you just take it the applied moment. Okay, so if minimum eccentricity value, it's mentioned that calculated eccentricity is larger, then minimum eccentricity should be ignored. It should not be added. It should be ignored. That means that if the problem would have been like 1500 kilonewton and moment is given as 100 kilonewton, in that case, means moment due to minimum eccentricity should be ignored. As 45 will not be there. You will be deciding for 100 kilonewton only, 100 kilonewton meter and 1500 kilonewton of axial load. Okay, understood. Now let's see how SP16 provides us the calculations. Okay, I told you that the interaction graph is provided in SP16, so you just please download it. You will see this is one chart 31. This is for compression with bending. That means we have compression as well as bending. It is for rectangular section only, and reinforcement distributed equally on two sides. That means in this case, if this your column is something like this moment reinforcement is distributed only on the two sides, then this diagram or this curve is for that only. If your distribution is suppose it is a square and your distribution is along both the side or equally in both the side, in that case you have to refer to that particular chart. Okay, so there is a chart for all the four sides equally distributed. Also this is for only two side distribution, only this side and this side. And some other charts are also there where you have equal distribution of reinforcement along all the four sides. Now here you can see, just look at it, is similar. Pu by fck bd this side, and mu by fck bd square this side, and these are different graphs and these are different e values. Okay, for different e values we have. So these graphs are represented by nothing but p by fck. P by fck. What is p? This is the percentage of steel. This is percentage of steel, and this is grade of concrete. So these values are provided to you. Suppose you get some p by fck value, you find out mu by fck bd square, and correspondingly you find which graph it falls. And if it is suppose somewhere here, then we will be take the higher value. That is, suppose it is 0.00, this is 0, 0, 0.002, 0.04, this is 0.06, right? So somewhere if your value lies somewhere here, suppose yeah, after calculation your values lie somewhere here, then you will be taking the higher value, this one. So it will be p by fck is equal to 0.06. okay, so from this 0.06 into fck, if you do, you can find out the percentage of steel that will be required for the column. And for this is here, the drawing is also given. You please go through it, understand it, that where what is d, what is b. D is where the side where the axis of bending cuts, that particular side is the depth and other side is the width. Okay, and distribution of the reinforcement should be like this, and d dash is here, which is the effective cover of the reinforcement. Okay, and as is pbd by 100. If you try to find out what is the area of the steel, it is p as is pbd by 100. Okay, So this is important. So after that, let's go for our calculation. Here says that if d is equal to d minimum, d is equal to dy is 300 mm, and d b is 400 mm for our case, because just try to understand, this is our column. So here this side is 300 mm and this side is 400 mm, right? So we have seen that this is x and this is y, right? And we have so this is the y over here and this is the x over here. So here the x is 400, so we have the moment in the about y direction. About y, that means the moment is acting in this direction. This is my. We have calculated my in this direction, right, about the y direction. So this moment is acting about this, and dy is 300, dx is 400, right? This is the y depth in y, and this is depth in x. Depth is x. Okay, this is the dx. So now as you can see that our mm, axis which should be taken into account is the y-axis, not the x-axis, because here my we are taking, that is moment about y. So which axis we are interested in? We are interested in the axis y. So let's draw it again, only with the y axis. So this is the y axis, your moment is acting my over here, this is the d and this is the b now. Okay, so as per the drawing, right, as per the that particular graph. Okay, so as we can see that it's a rectangular which is 300 and 400, we can say that the reinforcements are provided on the two sides only, and also this is provided on the two sides because to take care of the moment, because moment will impart some tension, and that tension will be taken by the reinforcement. Okay, so as the moment is acting in this direction, so reinforcements are provided along this side. If the moment would have been about x direction, then the reinforcement will be in the other two sides, and if it's a biaxial moment mx and my, then reinforcement will be equally distributed all along the sides. Okay, so if you see that a rectangular beam has certain advantages of, for suppose uniaxial moment, so where suppose for this particular shape my is means my should be taken care of by some providing reinforcement, but mx is already being taken, probably is not required, because in this you can see that in this direction your width is less or the moment of inertia is also less, so you can relate basically everything. Okay, so this case, as this is a rectangular beam, rectangular column, and we have a moment, so we are assuming that we will provide the reinforcement only on the two sides, equally on the two sides, and this is also very less, is only 300 mm. So there is no problem if I do not provide any reinforcement over here and over here, because the spacing criteria will be met, so there is no issue in that. So that is why we have provided reinforcement in the other two side only. So suppose you have a pretty wide column, in that case we should distribute the reinforcement equally all along the sides, but as in this case it is not required, so we are providing only on the two sides, so it's your judgment. Okay, so here dy is 300, dx is 400, this is b. Now b is what? B is the larger side, that is 400, and d is the shorter side, that is dy is 300 here. And also I told you that about the axis, in which side the axis cut, that axis should be taken as the depth, right? As this axis, y axis cut this side, right? This side is dy, and that should be taken as depth, that is 300 mm, and here it is 400 mm, and d dash by d, it is nothing but 0.213, and then you will find out pu by fck bd square. Put the values, and the pu is equal to 2.2 into 10 to the power, I think that means basically 1.5 times of 1500 kilonewton. This is the pu. fck, you know, m20, ba and d values are already available, so you can find the pu by fck bd and mu by fck bd square. Both values are you can find out. Now as these values are available with us, we can refer to the particular appropriate um, chart, and then we can find out what is P by FCK value to find out the area of steel. Okay, so if you refer to this particular, see here, d dash by d is also important because these graphs are having different values of d dash by d. So if you see SP16, probably I should show you one SP16, then you will understand. uh, yeah, so this is the design aid for reinforced concrete IS 456 1970. It is called SP16. Okay, so you will find out different charts, tables for different beams, columns, etc. And here uh, I told you about the column. We are designing for column. So yeah, this is for column section. So you can find out solution is also, one solution is also given. So I see chart 27, compression with bending rectangular reinforcement with two sides. Here d dash by d is 0.05. This is for fy 250. Okay, and fy 250 d dash by is this value, and you can find out different value. And the next chart will be for fy 250 itself, but here d dash by d value is different. It is 0.1 now. Then again the next value we will see it is for fy 250, but d dash by d value is 0.15 now. Then for again fy 250 it is 0.2 now. So you can see that for different cases here all the cases are equally distributed on two sides. Then equally distributed for four side is also available. So this is for fy415, which is for our interest, and d dash by d, that means after calculation of d dash by d you will see that is 0.2. So which is more nearer to 0.2, that particular chart you have to take. Okay, so if it is d dash by d is equal to 0.2, you can see it is 0.5, so it might not work for us. This is 0.1, and this is for 0.15. This point is for 0.2. Okay, so you have to take it for 0.2. So like this you have to see and you have to check the uh, curve. Okay, you have to find out which particular curve or particular chart is important for you or required, and that particular chart should be taken. This is for fy 500. It is by d is equal to 0.05 here. So like this you have to go with this. Now as we have d dash by d is equal to 0.2, so we will go for chart number 34. So where d dash by d is equal to 0.2 and fy is 415, right? And we have chosen to distribute on the two sides itself. And then for different mu by fck bd value and pu by fck bd and mu by fck bd square value, we can find out what is the value of uh, percentage of steel, right? So for fck 250, percent of steel is coming out to be 0. 0.2 into 20, that is 4%. Okay, so you can see we had um, mu, it is 0.063, and pu by fckbt is 0.93, so you can see 0.06, so it will be somewhere here along this line. So and pu by fck is 0.9, 0.938, so around 0.9. So if you see 0.9 here, 0.9, this is point, sorry, this is 1, so it will be somewhere 0.92, 0.94, like that. This value is 0.92, then 0.94, then 0.96, then 0.98, like that, right? So we have 0.92. So 2 will be somewhere here, so it will be like this, and 1 2 3 4 5 6, so it will be somewhere here. So this particular curve should be taken. So here you can see that it is 0.2, so p by fck is 0.2 over here, so that should be taken for our case. So now if I take that, you can see the percentage of is 0.2, and then p by fck value is that value, so that is p by fck, p by fck is zero point 0.2, so p will be 0.2 into fck is 20, so you just put the value and it becomes 4. Then area of the steel will be how much? ASC is equal to percentage of steel p by 100 into gross area of cross section, so it is 4.8 into 10 to the power 3 mm square. So we need six number of 32 mm bars, and then we will see that A1 is around 4.823 into 10 to the power 3 mm square. So ASC provided is basically more than what is required. ASC series required 4.8 into 3 mm square, and what we have provided is 4.823. So we need 6 numbers of 32 mm bars, and then we can see how much a percentage of steel that we have provided, which is basically percentage of steel is 4.019 and requirement is 4, and it is within the range, that is 0.8 and 0.6%. The minimum is 0.8 and maximum is 6%, so it is well within this range, so it is okay. But as per IS code, you can, if you remember, it is said that we can normally go for 4%, not more than that, but as it's a design problem, so we are just trying to understand the design procedure, so it is okay. So it is 4% for now. Then spacing of the bars in the longer direction, you can find out it is 70 mm, and spacing of the bars in the shorter direction is 172, so it is basically both are same. It's not very large and not very small also, so it is okay. And then lateral ties, then position and distribution of the lateral ties as well as the spacing of the lateral ties, we have already discussed how to find out, right? The diameter should not be should not be less than 30, means maximum dia of the bar, 1/4 of the maximum dia of the bar, which is 8 mm and 6 mm. So we have provided 8 mm tie. Sorry, it should be less than 450 mm. That also 16 times of the minimum diameter of the bar that it tries to enclose. So here all the bars are 32 mm, so 16 times of 32 is 512 mm and 300 mm, so which should not be more than this. So that is why let us provide 8 mm of 25 mm center to center, right? So we think we have already discussed all of this, and this is not we have discussed it probably twice basically, previous class also, and in the circular and rectangular, both in both the cases, lateral ties and vertical spacing, so it is not that big issue, I think. And other than that, the only part that is very important for you for designing an uniaxial column is the how to check for SP16. Okay, so I would suggest you to please go through and try to solve one or two problem, look and try to see how to use SP16, because it is very important. And in your exam, probably if you have an offline exam, so SP16 only the pages for the column discharge will be allowed to, you will be allowed to bring to the exam hall. And as the problem itself requires checking of the SP16, so you should be very familiar with SP16. And also we have various advantages of designing or using SP16. So it helps you to find out reinforcement for beams, slabs, columns, and it has various shortcuts, various charts, tables, which makes your design very easy. Okay, so I would suggest please go through SP16 and try to understand how to see, and also please go through this problem. This is not a big problem. We have taken a very long class, but the only thing is that if you are solving the problem, there is nothing much to do, but the theory behind it is a bit important. So please try to study and try to see all different clauses, and if you have any doubt, please let me know. And with this I would like to conclude today's class. Thank you.